All right, well, welcome everyone to the panel on sustainability, carbon neutrality, and HPC. This is a topic that, well, it's literally a hot topic, as well as a metaphorically a hot topic. We've got a great panel of participants. Andrew Chin from University of Chicago is on leave at Stanford, Nick Dubé from ARM, Thomas Eckerman from ULIC, Al Geist stepped in to sub for Satoshi Matsuoka, who unfortunately couldn't be with us today, and Jenna from Los Alamos. You know, I thought I would just frame things a little bit and sort of the if you will, the vicious circle of things that's driving change. You know, one of the things that's driving scale in our world is the fact that Moore's Law basically died. If you want more performance, you got to spend more money and build a bigger machine. And we certainly saw that here this week with new machines being rolled out. So that's sort of the free launch of faster and lower power is over. And so that's one forcing function. The other forcing function is, of course, the dramatic rise of generative AI and the fact that you know, we're seeing bigger and bigger systems built. In fact, I sometimes like to joke that I spent my career in HPC and I mostly thought I was a big iron guy until I went out to Microsoft and realized, no, actually I wasn't. And the scale has grown even larger since then. And so we've got these challenges of both rising scale, which is creating incredible demands for energy, and in some ways, energy that's not particularly environmentally friendly. You know, short-term answers are often gas generators. And so we're seeing demand, we're seeing challenges against the electrical grid. It simply hasn't been designed, at least in the US, and upgraded to keep pace with that demand. And then we've got all of these questions that we all know about the effects of carbon and climate change. And so when you put that together, I was tempted to somewhat tongue-in-cheek say, you know, we're pretty close to putting data centers in solar orbit because we need that kind of energy level, and maybe we'll do barbecue mode to keep them cool. But, you know, there is a limit on where we can go. And when we start to talk about gigawatt level scale for some of these things, we need to think fundamentally about some different approaches. And so I'll just remind you of what I said. You know, the free launch of Dennard scaling and Moore's Law is over. And there's really not much we can do about that. It's driving rethinking and architecture. I told some younger folks the other day that, you know, this may be the most exciting time to be in computer architecture in a long time because a lot of our operating assumptions are now thrown up in the air, and we need to rethink some ways fundamentally about next generation architectures. And after all, as we continue to shrink feature sizes down below 2 nanometers, you know, there's a limit down there at the bottom. When you get down to the countable number of atoms, the end of the road is near, and no exponential is forever, except in the textbooks. And then, of course, as I said, there's the rise of generative AI. And if you look at this semi-log plot and the computational demands to train next-generation AI models, that has grown exponentially as well. And so that demand is a lot of what's fueling the energy demands, but also putting pressure on the infrastructure. And you can find gazillions of these charts on the web. It's just looking at the rapid growth and the CAGR of data center power requirements and the energy forecasts that go with that. And this is really an unprecedented scale and a real set of issues about how we think collectively about how we evolve this ecosystem and what the bounds on reality are and how they collide with fiscal reality as well as environmental reality. And I'll just say one last thing before I hand it over to the panel, and I hope we have a lively discussion, is we're going to need at some point to think in some fundamentally new ways. And I'll just use this as an example. Here's a fruit fly, right? And we just recently successfully mapped the complete connectome of the fruit fly, and you think about what a fruit fly can do for a fraction of a watt, right? Vision, locomotion of various varieties, multiple sensor modes. It's an autonomous goal-seeking vehicle and it operates on a fraction of a watt. there's a lot we could learn from biology because there were existence proofs that we could do this a lot better that does not involve hundreds of megawatts of power and acres of machine room in order to do interesting tasks. So we need collectively, as they say, when you run out of money, you have to be clever and you have to think about the future. And so I'll just throw that out there as something, as a bit of a teaser as we talk about some of the pragmatics. And so with that, I'm going to hand the floor over to the first of our panelists, Andrew Chin.
Thanks, Dan. That was the perfect introduction because Dan talked a lot about causes and so on, and I'm not going to talk at all about causes. I'm going to talk about problems, maybe some solutions. Is that projecting? Okay, so I'm Andrew Chen. I'm at the University of Chicago in Argonne. I'm temporarily on sabbatical at Stanford. And I'm going to talk a little bit about some of our sustainability challenges and hopefully in this larger landscape, what role the HPC community has an opportunity to play in this cataclysm, which is AI and the power grid. So first thing I wanted to say is that computing power is big, and this is despite energy efficiency improvements. So this isn't to say that energy efficiency isn't important. We wouldn't have got as far as we've gotten without huge, right, many, 10 orders of magnitude improvements in energy efficiency since, vacuum tubes back in the 1950s. So it's been amazing. But despite that, computing power is very big. So we used to have tiny little chips that were maybe 10 or 20 watts. Now we have Blackwell. It's a kilowatt. It's one chip and up beyond that, right? We used to have pretty big data centers, right, around the turn of the millennium. Gosh, we thought 5 or 10 was a big data center. And now we have people talking about building 500 megawatt, gigawatt kinds of complexes. So we have 50 times higher power, despite the fact that we have these massive, unbelievable increases in energy efficiency. So nothing against energy efficiency. It helps us get more work done, but it's not going to solve this power growth problem. If you look at the kinds of charts that Dan referred to, this is one of my favorites. This is the Goldman Sachs projection. Because when the money people start predicting this kind of stuff is going to happen, that's a whole different thing than us technology people saying it's going to happen. But just to calibrate you, their low scenario is plus 40 gigawatts in the US power grid by 2030. Their high scenario is plus 120 gigawatts in the power grid, and their baseline scenario is 80. So that's a pretty crazy amount. So that's like, start building 10 gigawatts a year between now and 2030 if you're going to catch up to this. So what are the consequences of being big? Well, there's power grid challenges. I'll talk about some specific challenges that are appearing in a moment. But in the grid context, computing is no longer small. So in the Northern Virginia grid, today data centers are about 25% of the power grid. 25% is far from negligible. And once you get to 25% and you're growing at 25% a year or maybe even more, all of a sudden you're adding 5% and 5% and 5%. You're a big problem, right, in terms of the infrastructure. Today's cloud plus AI, some people are saying it was 25 with cloud alone. You put AI on top of it, it's more like 40 or something like that. I don't know what the number is. But just imagine, the projection is by 2030, the US power grid may be as much as 8%, right, data centers. If you're living in that world and you believe this digitalization goes on, right, then every year from 2030 on is 2% or more in the national power grid. This is an amazing, transformative kind of change if we're going to chase this. Now, it's always dangerous to predict exponentials 2 years out, much less 7 years out. But if we really believe that AI is going to become what we're hoping it will become, that's the kind of scenarios we're looking at. So what problems is this causing? This has to do with the role I think HPC has to play in this space. So HP simulation and AI training is causing power problems with the grid. So here's a plot from a very nice paper that, is Natalie here? Natalie and her co-authors wrote back in 2016, right? This is a chart that's taken from some measurements of the power system, right, in their facility, and it just shows some of the power dynamics that arise from starting a big parallel job, stopping a big parallel job, ramping up, running HPL, all this kind of stuff. And it's been a little while since I was an electrical engineer, but my estimation based on these plots is maybe it's like 6 to 8 megawatts kind of swing in these studies. And so HPC began to see these kinds of problems of large-scale computing used synchronously, right? The key is it's used synchronously, causing problems for the power grid. And my understanding is, and Natalie will correct me if this is not right, is the way they solved this problem is they called up the power company when something dramatic was going to happen, or they're afraid something dramatic was going to happen, and they would spool up a bunch of generation to make sure that they didn't bring down the grid. Right? Last week, I was in DC, and we had a panel on AI and the power grid and so on, and Ricardo Bianchini from Microsoft showed this picture on the right, which is a bunch of GPUs doing training, right, in this synchronous kind of a mode. But now the interesting thing is that this synchronous swing is, he didn't quote a number, but the whisper number is 15 megawatts, right? 15 megawatts. So this is the same thing. So first I wanted to say HPC should be proud of itself. We found this problem first. And there's a lot of cases where we're going to be finding these problems first, and we can continue to serve the community, the larger computing community, by finding these problems and solving them and laying the ground like we've always seen ourselves as doing. This is a good example of that. So human management mechanisms for this kind of problem won't scale. I would argue data centers likely need to internalize and solve this problem because the power grid has a hard time solving this problem, right? If you know a little electrical engineering and you think about trying to modulate a load at 15 or 20 megawatts going up and down with these kinds of second scale or sub-second scale frequencies, you know, the inductance along that line is such that you just can't control it from a distance and fix the problem. It's going to have to be fixed locally. So I think this is going to be an integral part of data center design. And that's something, for example, I don't know if we solved this problem in advance. Maybe Al's going to get up and say that we did, but I think these are the kinds of things that you know, we are facing. About almost 6 years ago, I wrote a paper based on some projections that Horst Simon had made about estimating what power we would need to build supercomputers at the leading edge. And this was based on 3 decades of 200 X performance in 5 years and a very predictable 3 times power increase. And if you plot a bunch of recent systems on this, like Fugaku and Frontier and Aurora and so on, you come to numbers that are into the 20, 50, maybe even 100 megawatt kind of range. So if you're going to continue on this curve, the technology headwinds notwithstanding that Dan already mentioned is probably worse than this. You're going to have to look at 3x power increase every 5 years if we're going to continue to stay on this curve. So I believe leadership computing will require large amounts of power if HPC computational capability is going to continue to grow in the ways that it's grown in the past. So this is the challenge I think that we face. So one of the questions for the panel was, is power going to continue to go up? Here's my stake in the ground. Yes, and very fast. Okay. So you might be thinking 300 megawatts in 2032. That's just a straightforward projection. One very interesting meeting I was at a couple weeks ago that LB&L put on was a meeting for data center flexibility. And there were people from the hyperscalers there who were building out these gigantic data centers. There were power grid operators there, Dominion, ERCOT, and folks who are struggling to meet this kind of mushrooming demand. There were power purchaser organizations that are trying to get sufficient clean energy, green energy, on tap and to buy it, you know, in a robust fashion. There were data scientists, you know, notably the Berkeley Energy Technologies Division that does projections of data center power. You guys all know these folks. And then there were a few data center grid researchers like me, very few, very few. But the observations that this group produced were, first, there's this huge global power grid crunch, right? Hopefully not news to you. And it's limiting power expansion. And the big challenge seemed to be mostly about who's going to make the investment and who's going to bankroll the risk, accept the risk, and you know, therefore reap the rewards. So who's going to pay for it? Everyone agreed that data center flexibility was the key to increasing grid capacity, and I'll talk about in a minute that it's actually a key to getting grid attached, grid connect for these new data centers, right? If you don't have flexibility, it's very hard for the grid to accept you. But there was a lot of lack of agreement on what does flexibility mean, right? The data center said, we're willing to provide it. The grid said, we want it, but they keep talking at each other, past each other as to what that means. So it's unclear what the technical spec for that is. It's unclear what the policy for use of that flexibility is. Like, do you get to control it or do I get to control it? And it's very unclear whether there's sufficient incentive because these are multi-billion-dollar data centers, which you probably don't want to sacrifice for my home's slightly better power reliability. Right, so there's a difficult financial trade-off. So super interesting, right? So power's larger than we are engaged in this. So what does this have to do with HPC, right? 40 gigawatts, 80 gigawatts, right? I don't know what the total HPC computing load is. Maybe someone will get up and say that, but I think it's smaller than most of those numbers. So I think HPC load actually has a story to tell here. So HPC load is flexible, and I think we have an opportunity to show the way for data center flexibility and to support grid decarbonization. I personally have worked on this for a long time. Here's a shameless plug for one of the things that I've worked on, zero carbon cloud. But it's not just me. Like many papers have been published. That's why I put ... in here. In the community, probably dozens, if not 50 or more. Isaac Huskin published a very nice paper on this recently, and then there's a paper in this conference between Northeastern and RECON as a collaboration that's even looking at incentive-based mechanisms to shape load flexibility inside of batch scheduled jobs. So our big advantage is the scheduling model and the resource usage model we have for our applications is quite flexible compared to a continuous VM in the cloud, or maybe compared to some of these training jobs, right? Or maybe some of the inference jobs. So I think that HPC has an opportunity to provide leadership in how to build and how to manage dynamic data centers in conjunction with the grid for both maximum capability and grid decarbonization. So there's a chance to lead here. I'm going to go through this fast because I don't want to go too long here. So one of the things that's interesting, you have to understand that the commercial folks don't necessarily want to be flexible. They are willing to be flexible if they have to be flexible, but the problem they're facing is quite severe. So if you add 80 gigawatts of load, these are some slides I showed at the National Academy's workshop. If you add 80 gigawatts of load, you might be thinking you're harmonizing it with this complex generation mix on the right. So that's solar, wind, natural gas, and so on. And in order to do that, you're going to have to add about 20 gigawatts a year, and you must accelerate what we're building right now, which is mostly renewables, right? So this is what the EIA says we're adding to the grid. It's mostly renewables that are growing in terms of capacity. Coal is going slightly down, and natural gas is going up a little bit. So now we have to really do the following challenge. We actually need to match this new 80 gigawatts of load, not to that same mix that we had. We have to match it to this added mix. The incremental version of this problem is matching it to this very volatile, nasty renewable generation, right? And if the data centers show up and they say, I just want continuous supply, they're foisting this huge problem off onto the power grid, and the power grid is going to have to solve it. Power grid can solve it, but it's going to cost you, right? They're going to charge you a lot more for power. So the problem is data center growth is a grid renewable integration problem as much as it is a reliable power problem. Okay. There's this idea that these dynamic data centers can increase the grid capacity, efficiency, and reduce cost. So we did a study of the EIR grid, that's Ireland, the Dominion grid, and so on. And basically, if you have a certain amount of flexibility in your data centers, like maybe 20%, it turns out you can dramatically increase the capacity of the grid. That is the number of data centers you can allow to increase. It was in excess of like 50% more growth in the next 5 years in the EIR grid, and it can be those kinds of numbers in other areas. So that's why all the excitement about these kinds of dynamic data centers or data center flexibility. And HPC can be the leader for that. Of course, when you do it, there's all kinds of interesting research questions of how to do it. That's what this long laundry list there is. And most important, you have to avoid this thundering herd problem, right? To use the internet analogy, which is you can't have everyone controlling their data center in an uncoordinated fashion. Then when the green power is in excess supply, everyone jumps for it, like the thundering herd, or everyone goes away at the same time as well. So you need some coordination. Okay. So I should wrap here, but I just wanted to put up my prediction slide. So I think that we're going to see continued power growth of HPC. My prediction is that top HPC machines will be as much as 250 megawatts by 2030. And I don't think it stops there. I think it goes beyond to even gigawatts. So I would encourage the community to think about how we can meet these kinds of challenges by making that kind of power consumption sustainable. Can I hype my?
Quickly.
Wait a minute. We have a new project trying to look at this. We have a small project funded by OAC trying to understand how to collect sustainability data from individual HPC systems in a fashion that isn't onerous. I mean, not all of us can hire 100 people to do the job like these big hyperscale companies do, right? So we're trying to figure out how to standardize a small number of metrics and a small amount of data that we could ask each of you to report, and then we'd roll that up and report sustainability for various data centers and activities. So if you're interested in that, please contact me or my student, Varsha Rao, who's working on this. Thank you.
Great. All right, thanks, Andrew. Next up is Nick Dubey from ARM. I mean, I will just opine as he's coming up. OpEx for energy has become a dominant issue for many people, and as Andrew said, it's only going to get worse. Nick?
Do you have diet or? I did, actually. Oh, I don't know. It's fine. Take it.
All right. Good afternoon. So I'm Nick Dubey. I'm now SVP for System Engineering at ARM. I used to be, most of you guys knew me as the CTO for the HPC business at HPE. Really excited to have joined ARM recently. As you know, ARM is known as a company that builds a lot of chips, very energy efficient chips. And just to give you an idea, ARM touches 70% of the world's population every day. So it's not just about Apple laptops, but it's also true processors that are hyperscalers. It's true smartphones, cars, TVs. So it's pretty much everywhere. So to today's topic, this is a chart from epoch.ai that's showing that GPT-4 models, and basically we're on a this is a log scale, right, on the y-axis. And we're in a very fast growth of basically flops intensity. GPT-4 is actually training GPT-4 consumed more than 1 week of Frontier, which used to be the fastest supercomputer in the world as of up until this week. So AI is very much of a supercomputing workload now because it's a strong scaling workload. And what's interesting now that I'm working with a lot of large AI customers is that they're learning a lot of the old tricks that we've learned over the last 2 decades. So for instance, joking aside, but it's actually true, must have forwarded at least 3 to 4 times like Gary Gratter's paper on checkpointing to these guys, so they actually learn how to checkpoint, how often, how big, and those things. And there's a lot of that. The AI community now is, and they're a bunch of kids that are all overpaid, but they have a lot to learn from the HPC community and to what we've learned over the last 2 decades. But interestingly, now they're learning how to go about running workloads at scale and how to build systems to do that and how to write software and runtime environments. They're driving a huge influx of money that will help the HPC community basically by having access to photonics. There's so many things as an HPC guy, I've been dreaming about for over a decade that are now about to happen because of the influx of money that large-scale AI is now driving. So it's not all bad. One of the other kind of hockey stick curve, I kind of like that one on the right, that's showing that now all the data centers in the world actually have a power consumption that's larger than Italy. So there's only 4 countries in the world today that consume more power than the sum of data centers. So this is very real. But here's what's even more real. We have a reliability or resiliency problem. This is a little chart that's just an Excel chart. Okay, so if you map out, basically you run those curves for a job duration of 24 hours and a failure recovery time of 1 hour. Most clouds will give you an SLA with 95.5% uptime. So if you're running a 1 GPU job, you're fine. 90% of your job will complete. You'll still be within SLA. If you're running a 10 GPU job, you're like at 30% and still be within their contract. So you really want a cloud that's going to give you a 99.9% SLA, which not all of them do. And then even then you're at 80% of your job completion. But when you go to 100 GPUs, to 1,000 GPUs, or even to 10,000 GPU jobs, you need 7 nines of reliability to complete 90% of your jobs. Now, this is not what's happening. What we see is that Alibaba, these guys published that article that probably many of you guys saw, and it's a fairly large system, right? It's a baby system as far as we're concerned in HPC. It's 128 GPUs, and only 56% of their jobs complete successfully. That's kind of an embarrassment, If Al and I had built Frontier like that, and if he had accepted Frontier on a job succession rate of 56%, I think we'd be both out of jobs. So we need to be better than this. Meta is reporting, there was an article that came from Meta, and it's 16K GPUs, right? In our community, 16K GPUs is something we know how to build. But what's interesting is that the hyperscalers and the AI shops are mapping, the key number for them, it's called, the acronym is MFU, Model Flop Utilization. Most people start at around 60% of MFU. But when they account for scaling the model, they drop below 50%. When they account for the failure rates that they're seeing, they drop to the 30s. And what they're seeing is that if they don't implement better reliability and better resiliency in the model, they're going to drop below 30% of MFU, which means that in the low 20s, that means that they're paying for 5 GPUs and only getting 1 out of throughput. So my big take on sustainability today, initially I was thinking of coming in and giving the pitch, we need to build data centers close to cities so we can do heat reuse and everything. I was like, no, that's not the biggest thing. Basically, we need to build better systems for AI. The systems we do today, they're just plainly bad. So we need to build better reliability in the AI systems from the get-go. That means borrowing from supercomputing technology, liquid cooling, properly designed power subsystems. We need to have the runtime that will basically detect silent data corruptions, that will be able, a lot of stuff we've actually deployed in the largest supercomputers. And then we really need, so basically drive as much of reliability as you can, but then build resiliency from the chip to the runtime. And by that, what I mean is, most of the runtimes in AI today, they're deploying in a bulk synchronous way. And why are they deploying in bulk synchronous? Because they borrowed from the HPC community, right? It's MPI runtimes, that's what we have. And that's what we deploy when we're doing, large energy physics and everything, and the physics is bulk synchronous. But if you think about neural networks, they're not inherently bulk synchronous. We have a way to actually train them in a far more synchronous way, which actually will probably make them a lot more resilient. And then if you think about the failure domain, losing a GPU or an SoC worth of training for one epoch is actually probably not statistically significant. So if we can implement better, more granular checkpoint methodologies with hot spares and being able to bring that up on the fly through the AI runtime, we're probably able to get those workloads to keep going without having to do a full stop, reload from checkpoint, and losing all of those GPU hours and all of that energy because we basically have a poorly designed system and runtime. So my big message to you guys today is, let's go propagate a lot of the learnings that we've done in this industry. Let's go embrace those bunch of new generation of guys that are people that are building large-scale AI systems. Let's go design better systems. And with that, I don't know if you saw the little QR code. I'm hiring, so if you want to scan it and apply, that's my pitch. Thank you.
All right. Thomas?
Okay. I can try this one. Okay, works. Okay, so I thought that it would be difficult for me to add to this global view something new after several of you have been presenting this. So I try to take a more local view what an individual center could do. So of course, using the Jülich Center as an example. So things that I think most centers already do, or at least target for, is to actually improve energy efficiency at different levels. So starting with procuring energy efficient hardware. So for some reason, our Green 500 #1 spot was, image was lost, sorry for that. Then, of course, the next level is to look at the data center, so we see what we can do here, improving PUEs, making sure we don't waste too much water that we need for the cooling, Then, of course, in terms of the energy consumption, we go for procuring renewable energy, and by trying to reuse the waste heat, of course, we can kind of double the effect that we can use the energy twice. Then also, of course, we need to look at system operation. What we see is that even idle nodes consume quite some power, so it might be useful to switch them off if they are idle for quite a while. We can look at things like energy-aware scheduling and, of course, tune our operational parameters. And last but not least, I think what we are all doing is we're trying to make sure that these systems are really used for good purpose. So through peer review system, we ensure that there's good science being done on that. Of course, there are other uses for systems which we try to avoid or which have little benefit, like and wasting a lot of energy, like crypto mining or things like that. This is having in mind that, of course, whatever we do, there is an environmental impact of computing, and at least we must make sure that this is done for good purpose. So example of a system that's upcoming in Jülich is the first exascale system in Europe with around about 24,000 Grace Hopper GPUs. We actually had to build a new data center for that. You see the environmental footprint. We will have to provide power of 30 megawatts. This is not what the system will actually use, but it has some headroom for expansions. PUE is 1.15 is what is contractually promised, but actually we hope that we will end up slightly better than that. We'll have glycol-free cooling, things like that. So you can see the data center from the top. It's a modular data center, so it will be built from containers which come pre-filled with the machines. Despite all that, of course, what we're doing has an environmental impact. We consume power. What we expect from that system is to have around about 11 to 12 megawatts on average. Still, half of that when the system is just doing nothing, and 18 megawatts roundabout when running HPL. So we consume energy. Of course, the data centers also consume space. It's quite a large concrete slab where the center is building on. We're using river water. Actually, we have a new generation of chillers on the roof that will consume way less water than the previous generation, where we, for a system of that size, would have around about 100 cubic meters per hour. So that is now how a fresh picture of how it looks today. So we're in the process of building things up. Containers roll in almost on a daily basis currently. So we expect to finish that in spring next year. So I mentioned waste heat usage, so we're also investing in that. We have the Jülich Research Center, where I'm coming from, is part of the Jülich Research Center. So Supercomputing Center is part of this research center with more than 7,000 employees and a lot of energy hungry and experiments, and also in demand of quite some heat. So the campus has an average demand for thermal energy of 7.5 megawatts, and that in a way fits quite nicely to what the exascale machine Jupiter will be able will at the end provide in terms of waste heat. So we start with a highly efficient heat pump that will pump up the waste heat that we create with the system, which will of course only have 40-something degrees Celsius up to the 95 degrees that we are running in our high temperature ring. And the idea of that is to really reduce the other sources of heat that we have on the campus currently. We have a gas-fired combined cooling, heating, and electrical power. system which is in a way quite efficient, but if we can tune it so that it run it such that it needs to produce less heat, it can, for the same amount of gas, produce more cold and electricity. And of course, we are closely located to the city of Jülich, and there are also companies which are interested in getting heat from us, but that is probably something would take many years to set up an infrastructure for that. So the lifetime is longer than the lifetime of the system, and since we, as a public entity, we never know if there will be funding for the next system or how large it would be, this is probably an investment that we will not take on the short term. But this is now something that I think has been said before. We need, what we can do is to raise synergies that we can get by looking not only at single things that we can optimize, but also trying to, looking at making leverage of intersector global system approaches. For example, in scheduling of jobs, we could take into account, we know that certain job classes have higher power demands than others, and we know that at least in Germany we have the situation where from in certain times of the day or week we produce more renewable energy than the grid can actually carry, and that leads to sometimes even negative prices. So you earn money if you consume energy, and that is something that of course could be leveraged by coupling things. So we would on the one hand make sure that let's say windmills don't have to be switched off because the grid can't carry on the energy, and at the same time get very cheap energy for that. Probably a bit more difficult, but in the same direction is that we could also see if the waste heat that we deliver to others, that the demand also varies, of course, from season to season and also during the daytime, and that could also be used to adapt scheduling policies. This would be a market-driven approach. Of course, the market cannot do everything. So there is also a regulatory framework. To give an example, Germany has this year started an Energieeffizienzgesetz, one of these nice German long words, which means it's a law for improving energy efficiency in general, and it has a dedicated chapter on data centers. And this is to be applied strictly by all data centers which have a power of more than 300 kilowatts, so well, almost everything, I would say. So it has requirements for the PUE, not too hard, I would say 1.2, but for, let's say, air-cooled data centers, that might still be challenging. We are actually forced by law now to use renewable energy, 50% now, and from 2027 on even 100%. And we are also expected to reuse a minimum fraction of the waste heat for other purposes. For older data centers, this is 10%, but for data centers that are newly built, this rises up to 20%. And last not least, we are also required to annually, or each data center in Germany is now required to annually report the KPIs coming from this law. So it's, yeah, we love bureaucracy in Germany. You can see an example here for that. But I think here it's actually for a good purpose. Thank you.
Thank you, Tom. All right, next up is Algeist.
Thank you, Dan. Oh, that's not an MP, that's not a HDL. Carefully to make sure that we got an HDMI
It
sitting.
was on the table before. Yeah, it must have fallen down.
There we go. Do we have to push a button? Or will it automatically find us? Try it one more time and see if it'll resync.
I have a dongle if you want.
Seems to be syncing here, but it's not syncing anywhere else. Let's try to see just in case it will work. Who knows? Miracles do sometimes happen. And it does. All right. Sustainability forever. All right. So much like we've heard already for a few of the speakers about the crisis as opposed to all of the solutions, I'm going to be, each of us has kind of picked a different thing. Andrew started out by saying we're going to need gigantic amounts of energy, and Nick said, and resilience is going to be this huge problem, and then we've heard about reusability being really important, and one of the questions that we got asked as a panel is, and what are some of the top order metrics that we must be tracking if we're really interested in sustainability? And so I wanted to throw that out on the table because so many times we say the important thing is how much energy I'm using. Well, that's a measure of the amount of energy, or we could say the amount of carbon use, or the amount of water that our sites use per unit time. But that's really the wrong thing, because if you go and ask Copilot or ChatGPT, well, how do I make that less? They'll say, well, just turn the computer off. Then it won't use any of those things. So the real metric that we need is to find out what is the purpose of these HPC systems and put that in the numerator. For me, at a leadership computing facility, it's how much science gets done. If I can somehow improve my application algorithms so I can get twice as much science done and the machine is still using the same 20 megawatts, I've actually improved sustainability by getting more work done for that particular case. Or if I'm training AI models, again, there are ways of balancing out the useful work over the energy. So that's kind of the first thing. This little diagram at the bottom was just sort of eye candy, but it actually does show all the different steps, and we'll talk about those at the very last slide. I was told that I could only use 45 slides or less. Actually, it was only 4 or 5 slides. But the application improvements is one, system, and so forth, and we'll get to that on the last slide. But, so the first slide was really the sustainability crisis itself. We talked a lot about our particular sites or our data centers, but what is the real issue that we're trying to do with sustainability? And the one that I have firsthand experience with recently, if you've maybe seen in the news about all of this flooding that had happened in eastern Tennessee when Hurricane Helene came up there, and that went right by the town where I live. But climate change really is ravaging the world. There are all these floods in America and in Europe, Asia. We've got, I turned on the news earlier this week, there are all these wildfires burning on the West Coast and on the East Coast, all these storms and hurricanes that are going on. All these are caused by increasing greenhouse gases, but I would claim that the data center power is not the dominant source of greenhouse gases today. But what you're seeing from all of the panelists up here is the prediction is from 2024 over the next 10 to 20 years, that's going to grow a lot. So if you think climate change is bad right now, we're going to make it a lot worse if we don't get a grip on sustainability. And that was just kind of a slide to make this point. Now, the very bottom bullet, though, is to say, well, yeah, but all those curves that show exponential growth over long periods of time is what Andrew was saying. It's really hard to say that An exponential is going to exist for 7 years, which is some of the predictions, even more so if it's going to be 20 years that you're trying to predict an exponential. So we also need to consider in terms of investments, particularly when you have power companies that need to spend trillions of dollars to make a much bigger energy grid. What happens if that AI bubble pops and suddenly you don't need that? Next up topic is energy efficient computing. And again, agreeing with what the previous speakers are saying, it helps, but it's not actually enough. So Oak Ridge has pioneered like a 200x improvement in energy efficiency from the time that we were building petascale HPC computers to exascale. And you can see from the diagram there just how that actually is improved. But why is it not enough? Well, the compute performance went up by a factor of 1,000, but the energy efficiency didn't go up by 1,000, only went up by a factor of 200. So you can see that the power consumption continues to grow in our data centers, and so that's what drives this need for more energy being generated on the grid. So energy efficient computing, it's good. It's something that we're going to need to do R&D in the future, but it's not going to solve all of our problems. Something none of the speakers have really talked about yet, but I wanted to spend a little bit of time on, are two things, and none of them have talked about those yet. One is carbon neutral, and the other is the sustainability crisis in water. What do these data centers use when it comes to water? And so I want to talk a little bit about that. So it was interesting to me when we had Frontier up here running, and it's been running for 2.5 years now, so we have a lot of metrics on what it's using. And so, you know, cooling towers, you see them on the roof of this diagram here. This shows a picture of our data center. And in fact, you know, one of the things I like to point out is that Frontier is this tiny little black piece right over here. But this whole big thing is all the data center. It's a huge amount of infrastructure that's required to run these things. But you have all of these cooling towers sitting on the roof, and they work by evaporating water. I mean, so water gets evaporated, it's gone. It came out of the water pipes, and now it's gone. How much do you lose in a data center? Well, it turns out that in our data center, we use about 100,000 gallons a day that are just evaporated into the air. Now, we use a lot more water than that, as you were saying, pumping the water out of the river. How much is that? Well, the Ornell Data Center pumps about 6,000 gallons a minute through Frontier to keep it cool. But out of that, another 100,000 gallons a day is just evaporated into the air and lost. And when my daughter sites heard that, they kind of chuckled and said, oh, you guys are doing a terrible job. And they went and looked at their own measurements. And it turns out that all three, LCAP, Frontier, Aurora, so the idea of a rule of thumb is for a megawatt computer, it takes about 100,000 gallons of water a day is just used up and gone. So then we think about, well, we want to be able to run these machines perhaps with small modular reactors or nuclear reactors, try to get to this carbon neutral. We run into another interesting thing. I went to the internet to try to find out just how much water is used for those generators. And so it turns out to generate the power that we require for machines like LCAP and Frontier and Aurora, it requires another 300,000 gallons of water, of makeup water that you just lose every day just to cool the reactor, the small modular reactor. And that produces electricity that heats up your computer, which requires another 100,000 gallons of water to cool it down. So you're talking about 400,000 to, 500,000 gallons of water every single day that's just lost to the atmosphere. So this is part of the water crisis of these big machines. And I was out on the show floor the last 3 days looking at the dry coolers that they talk about. But when you look at them, they don't handle the kind of scales that are needed for these large data centers, like an exascale data center or a nuclear reactor. And that's why big power plants that build those big water towers use water cooling to do their. Now, let's talk about the crisis for the generating companies to actually build these things. So other zero carbon energy sources, not including the satellite that orbits the Earth and produces solar power, but hydro, solar, wind, waves, et cetera, the kind of big things that the power companies say, well, you know, they're not available 24 hours a day. They're not available on demand when your application fires up on the big computer and suddenly in a few seconds, as Nick was saying, there's this huge load and it's like, I'm sorry, but the wind's not blowing right now. So nuclear is oftentimes one of the things that the power companies want to look to as a load that they can put on there. This is a little diagram that I drew, I got to kind of give you a feeling for two things: how much power these small modular reactors, microreactors, and large-scale reactors generate, but also how much it costs the power companies to actually build one, because we talk about how expensive the big computers have gotten, where, you know, something like Frontier was maybe $500 million, but you see Microsoft spending several $billion, but even, you know, a small modular reactor is, you know, $6 billion to build the plant that runs it. The small microreactors actually don't cost $1 billion. I actually was very interested in seeing if we could build something like that at Oak Ridge to power, say, the next generation of computer after Frontier. It turns out it takes about 6 of them to generate enough electricity to power a Frontier-sized machine. And then you have to have a building that is nuclear qualified because it's a nuclear reactor, which is way more expensive than just your standard house. And so when you put all that together, it's like $1 billion to be able to power your next generation computers with these small reactors. So there's a high cost of nuclear power plants. So that's our crisis in water, sort of our crisis to the power companies. And so for our last slide here, answering another one of the questions that Dan said, you know, what are the R&D that's needed to shift these dynamics around for compute sustainability? And it's really a multi-pronged effort. You've heard it from a lot of the people here already. At the building level, you've got to try to come up with much more state-of-the-art, energy-efficient data centers. There at Oak Ridge, you know, our PUE, you were talking about that the government in Germany was requiring you be at least 1.2, we've actually got our annualized PUE down to 1.03, which is sort of one of the best in the world.
We should talk.
Once it gets below 1, then we're going to be doing great. Yeah, 1 is the theoretical maximum. The second is the system. So trying to make the system more energy efficient. And that's where the 200X came in, but the 1.03 was sort of on top of that in terms of trying to improve sustainability. But the third one is one that everyone in this room can really help with, and that is application level. So how do you get more of whatever it is you're doing, whether it's AI training, whether it's doing science, how do you get more of that done? It can involve scheduling, it can involve improvements to optimize the cooling or the energy consumption, making sure it's during the time that loads are available, or not, or balancing the loads by running one application that uses a lot of energy and running at the same time one that has a small amount of energy use together on the machine to keep the energy balanced across it. It's all about asset life, so how long does the computer last, and also the user behavior. How do you train the users? Right now, particularly in a leadership computing facility, a lot of times everyone is only interested in going as fast as possible. They're not really interested in saving any energy. So how do we get the users to start thinking about how to be more energy efficient in the way they design their applications? And with that, I'm going to step aside and we'll ask questions later, and we're going to let...
Can I ask a clarifying question?
Sure.
The 300,000 gallons number for the reactor?
Yeah. It's
Cooling and energy generation?
It's simply thermal efficiency. It's about 30%.
Go ahead, Jack.
See, can we get...
Cooling and energy efficiency and generation, because it's steam-based generation, right?
Yeah.
Both.
It's at 30%. So if it takes 100,000 to cool it, it takes about 3 times that to,
Oh, I see. That's
Where are we,
That's for a 100 megawatt nominal unit, or?
are we not?
no, that's just for running a 1 exaflop system, about 20 megawatts.
20 megawatts, okay.
Yeah.
Let's see, we need to figure out how to get the other slides up.
And I made up these slides last night.
Whose machine is this?
So I was glad.
No.
You know, read what everyone else had asked. Sometimes, you know, every panel says the same thing, and I wanted, that's why I went through and picked out water and other things, nuclear reactors, so there would be something new.
Yeah, I'm not sure.
Oh, there we go.
Okay, here we go. All right, last, sorry about that, is Jenna from Los Alamos.
All right. Hi, everyone. So I have a little different take than the rest of the panel. I actually sit within our operations, within our sustainability program at the lab. So as probably most of you are over on the compute side or on the science side, so you can kind of see how far away our computer side and how far away our science side is in our org chart from our operations side. So I think that's a really big thing, is how do we connect our operations? I mean, how many of you know your operations team or know where your power's coming from to run your computer? Yep. So just a little bit about LANL, just to kind of orient you. We're a pretty big site. We're actually about the size of Washington, D.C., so that's pretty big. We also have, you know, I basically consider LANL like a small town. We have our own roads. We have our own steam generation plant. We procure a bunch of power with the county. And we have water, wastewater plant on site, we have electric lines, we kind of have everything, and our group in utilities runs that. So I figured I'd start with, again, focusing on our HPC and how the utilities program and how LANL is working to make sure that we are prepared to provide HPC and other computing complexes with enough power and water to make sure that you all can do science. So this is our forecast. Again, we do forecasts for our power, you know, about 10 years out, but this one is specifically for FY27. And you can kind of see how much power we're going to need for our facilities and how much our computing power is for our whole area. So LAC is the county, so like I said, we do a power pool with the county up in Los Alamos, and then about a third of our total power needed is for our computing. So it's a really big focus to make sure that we can provide you all with that power. So I'm going to take, like I said, a little different perspective, but also have some, I think, some good news to end our panelist talk. So this is our Executive Order 14057, and it is basically requiring federal facilities to go to net zero by 2050. So that is saying that every single building has to be 100% net zero emissions by 2050, and there's a lot of different steps to get there. But one of our main things is how do we make sure that that supercomputing facility can also get to net zero. So these are some of the goals, and you can read through those. And this is how LANL is hoping to get there. These are our 6 strategies of really making sure that we can figure out how to get to net zero by 2050. We're really focusing on the first 3 within the next couple years. So greening the grid to meet scope 1 and 2 emissions. And I'll go into like what we're actually doing to make sure we can get that green power on site. Building the next generation of facilities, so putting that in our design standards to make sure that all new facilities are net zero ready. Connecting with since we are a big science lab, figuring out how we can connect with our scientists and bring some test ideas on site. Say how can we, do better energy and water. Ensuring on-site carbon-free electricity production, making sure that our existing facilities, that we retrofit them correctly, and then adding resiliency. So figuring out how do we get that 24/7 reliability, which has been talked about by the panel. So again, some more good news. One of the things that we are doing at Los Alamos to make sure that we can get that carbon-free electricity is we are actually partnering. So this is like the Four Corners. You can see the little picture of New Mexico down there. But in the Four Corners area, we are actually, they're going to be building a solar array. So it will be 120 megawatts will come to us. We're hoping to get it completed by 26. So basically, when we have a bunch of folks complain to us, why am I electrifying my facility if the grid isn't green? This is how we green the grid. We have to invest in these big projects. And New Mexico is pretty sunny, so it's a great place to do that. With this project, this is basically what we have to do to make sure that we can get to net zero. So that orange line on the top is basically if we do nothing, that's where our emissions are now. And then slowly getting rid of our coal power, and again, bringing on that solar. You can see that big white area is the avoided emissions that we'll be getting. So that's kind of our hope getting to 2050. So now I'm going to switch over to water, because water is obviously a big thing. We are in the desert, the high desert, so we really care about water. Again, we really know that water scarcity is becoming a bigger issue. We've seen that with climate change, and we want to make sure that we can also have our resilient infrastructure. So what we've decided to do at Los Alamos is, this is our water balance. And basically, we run our data center, our biggest data center, with reclaimed water. And basically, we do that with our SURF facility. So it's the Sanitary Effluent Reclamation Facility. And we basically take water from our wastewater plant, super clean it, and then that 100% powers our supercomputer. So that goes into our cooling towers, and we're able to basically claim that we have approximately 100% reclaimed water. So that's really awesome too. We produced 48 million gallons in FY24, and that was able to run the entire facility for that year. With that, because this water is so much cleaner than our potable water, we're actually using a lot less. So if we used just our standard potable water, it'd be 161 million gallons a year. So you can see there's a huge savings there. And a little, about 800K of savings in terms of dollars. Unfortunately, water is cheap in New Mexico, so it's not a huge savings, but it's still something. So SURF, we're hoping to expand it in the next couple years to get to it to produce 100 million gallons, so basically doubling the amount that it produces. And that will be able to supply our other data centers that are on site. And we're also working on a project now. We have a linear accelerator on site, which I know is an HPC, but we're hoping to also use the reclaimed water over there. So we're hoping, as we grow, that we can be able to decrease our overall potable water footprint, but still be able to do the science that you all need. So I'd say to kind of wrap it up, I know we've had some doom and gloom up here, and that is true. But I think with the right regulations and with the right team, and if your site is really focused on making this a reality and making this a priority, I think it's definitely doable. So I wanted to give some examples of how we're doing it at Los Alamos. Thanks.
I'm reminded something like 25 years ago, which is an indirect way of saying I'm old. I remember being at a meeting where Mark Seeger, then at Lawrence Livermore, said, "I'd like to have a file system visible from space." Well, we have that now, folks, in spades. And so as we think about these challenges, here were a few of the framing questions I threw out at the panel. But I would invite those of you who have questions, and I surely expect there will be, wave your hand and one of the students will come around and hand you a microphone. But the big one people talked about is thinking about holistic system integration, and I see we have a question there. So please go ahead.
Go ahead. Yeah. Thank you. So I'm Ung Sin from Oak Ridge. one of the topics that came from Andrew's presentation and Nick's presentation was the word bulk synchronous workload, the flexibility of workload. So I do understand there has been a large body of those large body of research how to make that more flexible. So I would, if you don't mind, I would appreciate if you can kind of summarize that what would be the most promising approach to look into to make it more favorable to the grid. For example, like to make it more distributable or more, so we can more adapt to either the grid itself or really save us from the reliability issues we have.
So maybe I'll start there. I think Al and others might want to comment. On HPC, I think it's hard because on HPC, you have, when you're doing multi-physics simulation and you're time stepping and everything, you really need every single piece to get computed until you go to the next step, and that makes it hard on a lot of the mission codes. And really, then it's a matter of making sure we have reliable systems that basically don't go down, are able to sustain long multi-hours run. Because Frontier, you know, when we were doing LINPACK runs on it, it would swing in the grid by like about 15 megawatts, right? So that's, you don't want to do that too often. That's not a good thing for the power infrastructure. So for HPC, it's hard. There are ways to do it, and I'll let others comment on that. For AI is a different animal, and AI right now is trained bulk synchronous, but it doesn't have to be, if you think about how neural networks are mapped out. The other big thing, right, is that if you're doing large-scale simulation, you actually need to compute every single piece and have numerical accuracy for most cases. In AI, if you're dropping the weight and activation adjustments of a single GPU on one iteration, it's statistically probably insignificant. So if you have a granular enough checkpointing mechanism, you might just want to drop that, take your checkpoint. As long as you have hot spares, then you tee up the next GPU that you have in your system, in your scale-up network, because that's how those are being designed today. And then it catches up with everybody on the next iteration. So you would barely see it on the power signature of the system. The system would just keep going. Today we're not doing that, but that's definitely, for me, that's a very active topic that I'm working on, pushing my team to work on.
Did you want to say something about resilience? I'm going to go back to the other topic, which was...
Go back to the other question. I won't talk about resilience. I can talk about how you do bulk things a little more efficiently.
So the part of the question that I'm going to respond to is this question of, you know, people have written lots of papers about how to flex batch scheduled, HPC workloads. You know, what more needs to be done to really extract the benefit? I think that, some people will tell me when I get up and give predictions like 250 megawatts, they say, oh my God, we can't possibly afford that. Turns out power prices are dynamic in these future grids, even more dynamic in the future than they are today. And you can reduce your power cost in Texas by 90% by giving up 3% of the 5-minute intervals in the year. So the answer is, if you're willing to flex in that way, you can reduce your power cost by as much as 90%. So what I would say is what hasn't been done, I haven't seen it, happy to be wrong, but I haven't seen anyone express that kind of commitment to dynamic management, and that would be expressed both in how you operate your data center, it'd be reflected in how you give guarantees, like do I allow you to schedule 24-hour jobs, do I allow you to schedule 8-hour jobs, does that change over time, and so on and so forth. And then of course, greater selectivity in the power of the jobs you select. You select the power-intensive ones or the not power-intensive ones, and so on. So I think there's a huge dynamic range there, and it's largely being restricted by the narrow mindset that we have both in the traditional data center operations teams as well as scheduling formulations to make it not possible yet to tap the huge benefits that are there.
Very good. I think you were next, and then I think we have a young man.
Yeah, I'll throw in one other thing too, which is, there was a lot of work done in asynchronous algorithms in years past, and we essentially forgot it all. There are fundamental algorithmic opportunities to rethink a lot of these questions, and that's a challenge I would throw out to the community, because that's free lunch. If you find a better asynchronous approach, you can take that to the bank. Natalie.
Yeah, hello, my name is Natalie Bates. I chair the Energy Efficient High Performance Computing Working Group. Thank you very much to Dan and the panelists. You guys brought a lot of really great material. I want to take Nick's idea that we need to lead and link it with both Thomas and Al's idea of useful science. So Al, thank you very much for the top order metric, useful science per energy. I was, before you got up there, I was like, you know, this is the problem in my estimation with a lot of AI is like, what are they doing with this stuff? You know, we're allocating tons of megawatts of electricity. We're building huge machines. We're taking away, you know, useful silicon and using it to do what? Let's lead. Let's lead. Let's create a metric, all of us, that starts talking about what we're doing in terms of energy. I love that. Let's do it.
You know, there's an old line Dick Hamming said, the purpose of computing is insight, not numbers, right? Which is another way of saying that. Yes, go ahead.
Yes.
Here, yep.
Okay, so Mohammad Atiq, I'm from Fermilab. So I have a question for Al that, you know, you have that matrix for energy efficiency, how much, you know, science is done per total energy. So useful work, how do you measure that useful work?
Yeah,
And useful science, like what is the
and
measurement?
that's why people often just measure the amount of electricity that comes in their center and don't actually address it, because that is, you know, it's the metric we need to really drive forward and lead with, but it's so hard to measure by saying, what is my Fermilab, you know, linear accelerator calculation more important than the astrophysics calculation, more important than the material science calculation, versus, you know, just doing AI training? I don't know. You know, there's this weighted measures that we just don't have a good grip on, but I think that's the issue that we as a community need to try to address. I think right now, the way we address it at Oak Ridge National Labs is just from the statistics. You know, we run roughly 1,500 jobs through Frontier every day. And, you know, we can tell, okay, are we getting more jobs through it every day or not? That the jobs have already been pre-selected to be kind of the most important jobs for a giant computer. And so we don't measure one as being more valuable. But right now, the simplest way we do it is just how much science, how many jobs can we really get through it?
Can I just interject something? I wanted to say something while Al was speaking, because he talked about how much water is consumed by evaporative cooling by the data centers. And I think that there's a big move in the industry to eliminate use of evaporative cooling. There's
Dry coolers.
dry coolers, and I think some companies have already made a commitment that all of their future data centers, not to retrofit the old ones, but all their future data centers will not use evaporative cooling that destroys environmental water. So, so I would challenge, you know, anyone here who's building, designing, running a data center to look at that and see if it's possible actually to take that step.
I'll just add one thing to that, which is we in HPC have historically artificially constrained where we put these systems based on historical context, right? If you remove geography and optimize holistically, you get some different outcomes as well.
Did you have something
So
to say?
yeah, I'd like to add something to the question how to measure the quality of the science. So a traditional measure is to look at scientific publications, and that's something, for example, that we do in Jülich. We ask our users to acknowledge usage of computed time in their publications, and then we scan the net and see what's there. We would love them to be more active in doing so, but at least we get some kind of measure of
And the only
nature
trouble that we
papers and
have,
stuff.
you know, at any of our big centers is the time lag between when you get a really good publication versus that calculation you did a year ago to get it. How did you know then that this was going to be such an important paper? But I agree that, you know, with a time lag, how many great publications are coming out of your data center is important.
So, Al, you probably know what I'm going to say. When we don't necessarily need to compare physics between fields between themselves, but we may want to be able to compare within one field, are we doing the right scale? So when you were talking about the fact that GPT-4 is using a week of Frontier, do we need GPT-4 compared to GPT-3 or the previous version, and what does it bring, and should we be using that scale or maybe even lowering that scale within one field?
Yeah, that's a really good point. So it was the one I was going to answer, the first question about batch scheduling. If you have 3 or 4 jobs that can fit in the giant computer at once, then, you know, you could actually optimize the size of the job. If you think of the way almost any algorithm works, is it has a very steep climb in scalability up to a certain point, and then you keep adding more and more processors, and it continues to go a little bit faster, but not linear scaling. So it starts to bend over. So if you have 3 jobs, the ideal thing would be to pick it right up near the top of the kind of the linear scaling and not try to push it all the way to the end of the 8,000 or 10,000 processors. And then run the next job, again, up there at sort of its optimal scaling limit. And then the next job you put in, you do that again. And so there are some very clever things that this community could think about, how you can run more energy efficiently on the machine.
But Al, I think you're missing the opportunity here, because to the question, right, should we be using GPT-4 or going to O1 or going to better models? Once we get to AGI or artificial general intelligence, then you can just send that over to AGI and it will figure out how to optimize your jobs.
We just ask it how to do it, how to measure it.
Yes.
Hi. It seems like there's really great work happening at Los Alamos focusing on sustainability features on site. And my question would be, what do you think can or should happen to incentivize those on-site sustainability features from being to be implemented at data centers more broadly?
Yeah, that's a great question. I think with Los Alamos, some of it definitely, I think especially with our surf facility, it took a really long time, I think, to get that project off the ground because it was expensive and it's expensive to run. So I think it really came from the reliability standpoint, especially for us, is this is a way that we can ensure that we have water all the time. Like, we're gonna have our wastewater plant, and it's a way that we can reuse that water. And it makes, I think too, like, our community is very focused on sustainability. So I think, you know, we've had a lot of pushback, especially with Los Alamos' history, and people being like, well, why are you using my drinking water to run this like big computer that does all this, like, who knows what it does? So I think that was a big incentive. And I think a lot of them probably come from non-monetary standpoints. So I think if other facilities want to do something like that, I think reliability is a main one that really, I think, can help, especially with climate change. We don't really know what is going to happen to our water supply. And this is a way to ensure that you have water to continue to run your facilities. And I think for us, for the solar, it was kind of the same thing. Like, we had a coal-fired power plant that was shutting down in our state, and that's where we got the majority of our power. And it's like, okay, now what? And basically that community was like, well, we're just going to build a big solar plant. Do you want the power? And we're like, yes. And we did a big, you know, it was a big negotiation. We're working with Sandia Labs, and it was like a really nice joint effort to kind of have that connection to the community as well. So I'd say that if other sites want to do that, focus on community, focus on reliability.
Jenna, I had a question. You guys did this really nice study that went out to 2050 in your plan for getting to carbon neutral. I'm curious, what growth of electric power consumption is built into that plan? You said it was 30% computing in 27 or something, right?
Yeah, so basically our power forecast is pretty much, since part of that executive order is also that we need to electrify all of our facilities, and a lot of ours are run on gas or have their own boilers at the moment, so that's going to be a really big challenge of just converting everything over. So basically we're about doubling our power by 2050-ish, which is quite a bit, and that's like with new computing, that's with these other facilities, that's with other mission stuff, but it is built in there, and that's why we're building another power line going up to Lanel, because we need more power.
So are you thinking of running your computer mainly in the daytime when the solar array is running?
I think that's probably, we haven't talked too much about it yet, but I think that's definitely a big piece. We also have a steam plant on site, so that's really helpful to kind of balance that out, and a gas turbine generator. So there's definitely going to be a mix, and that facility will probably be like our backup power, I think, for a really long time too.
Al, your jobs will run really fast during the day.
Yes. They'll be ready to go.
But I think there's a greater opportunity there. And I'm not going to go back to make the colorful comment I made last year about people building data centers and consuming water in the Southwest. But Jenna, seriously, if you're going to change gas boilers basically for heating of buildings, why aren't you using the supercomputer to waste heat to actually heat your buildings?
That is another project that we're actually doing a conceptual study right now.
Do it. It's been done.
Yeah.
And it needs to set the example.
Yes.
We need to stop building data centers and farmland. Sorry, I'm going to make another comment. This is the stupidest thing we could do. We need to build those large data centers next to cities that or big campuses that can actually consume that waste heat. The Scandinavian countries have been doing that forever. We need to do that. There are many other geographies that can do that. If we do that for 6 months a year, we're able to reuse that energy, offset the carbon emissions, and actually heat people with it. We have to drive this change worldwide, please. Thank you.
Well, I'll opine one thing. One of the things I'd be interested for you to think about, both the audience and the panel, is the politics of OpEx and CapEx expenditures are different for government agencies than they are for private sector. And so some things are actually challenging in the public sector, not just in the U.S., but worldwide, to do that make economic or even social sense, but they're politically more challenging. So I'd invite some conversation on that, but please go ahead. Yep.
Hi, Simon McIntosh-Smith from Bristol Centre for Supercomputing. Nick, that was a perfect lead-in to the question I had for you. So our PUEs now are kind of tending towards 1. We're into diminishing returns, won't get much better. We're capturing all of our waste energy as hot water, so we can start to reuse that, and that's the next big piece where we can make a difference. In the winter months, some of us can use that to heat buildings, but if you're in a warmer climate or in the summer, we still don't seem to have great solutions for what to do with that energy. So what's the state of the art? What do we see coming up where we could actually use our waste heat the rest of the time, or if you're somewhere warm?
A great example of that is in Norway. They're using it to warm up fish tanks, fish farming. And with fish farming, you're actually almost year-round because the fish like to be kind of warm and comfy. So they grow, they reproduce faster. And what's interesting is that this facility produces the equivalent tonnage of fish for consumption, but also of basically fish fertilizer to fertilize the fields in the summer. So that, I think, processes, everybody's been dreaming about brewing beer on supercomputer waste heat for like a decade. So that's some usage that's close to HPC people. But processes, chemical processes, farming applications, those are all things to be looked at. Thomas can probably talk to, you had a project that was using what was it? It was kind of a super heat pump where you were basically using the waste heat with an adiabatic process at, where was it in Germany? Oh, it was LRZ that was doing that, I think. Yeah, LRZ was doing that and to actually generate cooling in the water in the summer months. So anyways, there are ways to do it, to use it.
There's a discussion I had with my colleagues which popped up, which is related to the rebounding effect. So it's a concept where people wanted to do fuel efficiency, so they made the car really efficient, but at the end of the day, that didn't really get the fuel consumption go down. It actually brought the more demand and go up. I was kind of wondering in HPC, if we things make more efficient, that's something that we should be worried about, or?
Computing is the case study for the rebound effect. Right? I mean, our computing has become cheaper, more efficient, more energy efficient by 9 or 10 orders of magnitude at least over the last 50 years. And what is the total power consumption of computing in the world? It's skyrocketed, right? Mm-hmm. So you know, absolutely, all of this efficiency is going to cause more consumption, and it's a reality of our technology, and we need to find ways to mitigate the damage of all that consumption that's going to happen.
Yeah, it actually has a name in economics. It's called Jevons paradox.
Yeah. Mm-hmm.
Let's see, who is?
Hello.
Yeah.
I hope this isn't a foolish question, but is there a reason why coastal facilities don't pump seawater instead of using drinkable water?
There is. The salt water corrodes the inside of the computer and causes a lot of damage. And then you also get deposits inside of the tubes in either your cooling towers or the computer itself, depending on where you have. You really want very pure water, as Jenna said, in the machines and in the pipes that are in the cooling towers as much as possible.
But there's a way to do it. The way to do it is not to pump the seawater in the facility. It's to put a heat exchanger straight into the ocean bed. That's what they're doing in Kajaani in Finland. And if you do that, you actually do your heat exchange in the ocean. And oh, by the way, the fish all end up hanging around that because, and they all end up being very happy. So then we can have an ecological debate if we should actually heat up the ocean or not, but that's.
We should debate that. That's one of the reasons a lot of people don't do it.
Yep.
And that's why you see a lot of nuclear reactors, for example. They'll put them near a very large body of water to just sink the cooling right into the body of water itself.
That kind of goes in, Jakob Lütgau with INRIA, the kind of goes in the direction I would also ask, like we see a bunch of challenges where co-design of some, co-location of some sorts would help. But I feel like there's a missing space to really chart out the different opportunities that are there. I think in the energy grid that you mentioned, there's opportunities to react to the swings better. We have the heat waste and the things that come, and also environmental factors like water, sun, or strategic factors. And I don't think that we really have a clear picture of what all of these opportunities are. And as you go through different geographies, you have different factors that are there. I think that is kind of a missing service to the community. And I have one other question. There's a little bit more to the life cycle than the operations, I think. We don't really take the manufacturing costs and things like this into account, and obviously there's challenges to get transparency into that, but I think that that is a missing topic that was here in the panel a little bit.
Yes.
So I can chime in on that. So, okay, so for AI, which is the largest growth in data centers, we have to decouple inference from training. So to your question about co-design, geolocation, and all of that, inference has to be closed to consumption centers because of latency and usability and all of that. Training has not. So to build massive training, AI training data centers close to populations, unless you're doing heat reuse or you're actually doing it the right way, actually doesn't make a whole lot of sense. Because training can be delocated, can be remote located. And the way the industry is not thinking about it this way. But if we were to think about putting training data centers close to hydro dams that would be supplemented with massive windmills and things like that, you don't care because you would save a lot on power transmission losses. You would co-locate with things where you'd be actually able to co-design with the environment with the power generation. And honestly, you run a fiber, you load up your data, you do your training kind of delocated. That would be a far more probably efficient way of just doing it to where you can get the cheapest power possible and without regards for how to reuse or how to optimize.
I think it's a great question and something we should all think about. I'm going to go a different direction with that. So recently, there's been a lot of popular backlash against the construction of data centers. A bunch of reasons, right? First is they don't necessarily add a lot to your neighborhood. They're not the most beautiful things, though many of us might think they're beautiful. And they consume resources and all these kinds of things. So there's been a bunch of proposals to build co-located sort of campuses, right, that bring in the fiber, bring in the power, aren't zoned for R1 residential housing, so you could sort of separate these industrial sectors and so on. So I think there are some opportunities for synergies there. But at a more basic level, I think, we've heard Nick talk about this, we've talked about coupling to water, we've talked about all these kinds of things. There are a bunch of different forces that work against each other. Some things you want to be close to because of the synergies of waste heat, for example. You don't want to pipe waste heat 100 miles, right, to a city. On the other hand, you don't necessarily want to be near the neighborhood and then live next to that data center. So I think it's a complicated set of questions, and if you look at them just purely technologically, you might not find the answers that are the right answers for society.
Right. We're going to give you the last question.
Okay. So I have one comment and one question. So in terms of comment, I want to add just that equation you put science per energy kind of. So I want to say, while this community has more concern on the environment or energy and something like this, actually our front edge computers, their lifetime is short. So something like a Frontier is like 500 million, you said. If it's just run for 5 years, it's 100 million per year. So my comment is, while we focus on the environment and energy efficiency, actually those are a lot of taxpayers' money, especially for DOE centers, right? So I think we should somehow can proportionate that cost into the sustainable metric, or some like probably the science done per dollar, probably all the cost included might be the better focus, for us. So that's one comment. And the other question, I'm interested in I'm also else, one bullet, you said we should somehow get users incentivized and then try to get involved in this energy saving effort. So can you comment on what kind of incentives, and then in terms of policy or funding, and what we can do to help, users?
Yes,
help
so
us? Yeah.
we've given that actually a lot of thought at Oak Ridge, because we're trying to be kind of on that cutting edge, and we've saved as much energy as we can. How can we save more if we could get the users involved? And what we're thinking about doing is, how do you incentivize them, particularly when they've been given time on the machine for free? So it's not like you're charging them more because they're not energy efficient. So instead, what we do is, we don't do this yet, but the two things we've thought about doing is one, perhaps changing their priority. Oh, you've thought about energy efficiency, you have a much more energy efficient algorithm, therefore we will bump your priority up in the queue for your jobs, or everyone's jobs that are more energy efficient, yet in some sense a bonus through priority. The second one idea that we're bouncing around is whether you might get, in some sense, time off. So your 5-hour run might only be charged 4.5 hours because you are using a much more energy efficient approach. So those are the two ways we've thought of trying to incentivize the user behavior, so then they would start to want to do it because they see it as a value to their getting their science done.
And if I could just tag onto that, one of the papers I mentioned, that was a joint effort between RICAN and Northeastern University, actually looked at a bunch of incentive mechanisms in the context of scheduling for Fugaku. And of course, it's the beginning. There's a lot of work that needs to be done, but I might encourage people to look at that nice piece of work.
Well, we're out of time. I want to thank the panel.
Okay.
You have one more.
Don't worry.
But I would encourage you as you leave to think about this. We all, as we think about problem solutions, and this last question was a great example of it, we think about them within the context of some bounding box. These problems, as Andrew rightly noted, are complex social, industrial, policy, economic, technical, and engineering issues. You got to see the whole board as you think about the solution. All right, thank you all.